adversarial networks. So let me explain that what is that logic. So here in this case, let's say if I'm giving a CNN network, it may be autoencoder which is having encoder and decoder network, decoder modules, and specific target which is called ground truth is available here. So on that, when I am training, whether it will go appropriate or not, in between, if I see the situation, otherwise if I see after 100 epochs and if it is diverged, like I said that it should not be overfitting, it should go appropriately. So that should be verified every time. Otherwise, if it is getting overfitting and data is that losses are keep on, one is decreasing, like training loss is decreasing and validation loss is increasing, so there is no point of further training. This kind of measures or this kind of checkings can be happened in the network itself instead of human verification. So it's a kind of supervisor addition along with the network. Some supervisor will be added. So here simple example, like if I'm having as if I am teaching one course and in that there is a mini project and let's say 15 students are there. And then I have given a specific project and a specific target to the students, and I ask that after 15 days I will evaluate your performance based on your project outcome. So if I see two ways are there, I can simply ask them to submit the proposal, this project output, or maybe demo after 15 days. That is one way. Other way is that I'm checking just their performance, their outputs, maybe every 3-4 days, and then whenever something wrong is happening, I'm just diverting, no, this is wrong, and correct it. If I'm supervising those process, this project execution, their training for every 2-3 days, so then I can train them in such a manner wherever they are going wrong direction, I can say them, I can correct them immediately, and they can go in appropriate manner. This is a process. The same thing is applied here. There is a supervisor which is nothing but a discriminator network is on top of the autoencoder network, which is autoencoder. As said, it is a generative process. Autoencoder is a kind of data generation network. That's why we call it as generator network. And then on that, if you are adding a supervisor, that is called we call it as a discriminator network. So in this, we are having a two networks. One is for generator network, and other one is a discriminator network, where discriminator network is always trying to supervise the generator. If I even just name wise, I think you can see that it is a generative network. That's why we call it as a generative. Adversarial means supervisor is in positive note, and a negative if you say that if opponent is there. If specific opponent is there, then only we can able to grow the means we can able to achieve the requirement. If there are no opposition, so growth of that particular system definitely will be less when compared to with opponent. And this is a deep network. That's why we call it a networks. That is the reason we call it as generative adversarial networks. And then why generative models, I have already explained, like where autoencoders are getting failed, it is going to solve by using generative adversarial networks. It has changed the game of autoencoders and shown the output variations, like accuracy wise improvement has shown very good improvements. Maybe, but it is not good for image super resolution. Generative adversarial networks were not good for super resolution purpose. With experience, we have seen that it is not improving the performance. Reason also I can give. Reason is that input and output very fine level edges improvements are required, but the generative adversarial networks can work for very superficial or kind of shape development and very fine level architecture, fine level details. You need to go for better losses. So this simple GAN or discriminator may not able to perform. So here these two are the images. One image generated by generator, and other image actually the you can say actual required target. So can you say that which one is a generator output and which one is the actual requirement from this? Anyone can guess? Left side one is the what, and right side one is what? With a, which one is the generator output? Right side one or left side one? Am I audible? First of all,
Yes, you're audible.
okay.
So if somebody who wants to reply, they can reply in the chat box or they can raise their hands. So,
They cannot speak, ma'am, here.
yeah, only host has the permission to.
Okay, okay. I think some chats
Yeah, some chat they will. Yeah, right side they are saying. In the chat they have written right side.
means right side one is the generated one.
Yeah, generated. Right side is generated one.
Just see that how can we say that? Reason is that see here these regions.
One person is saying left side is generated one.
Yes.
Arup
Yes, left
Nath
side
is
one
saying.
is a generated one, because if you see here, if you see the clarity wise, this is actually the one, and this is, you can say, generated one, because generated one, generator is trying to approach the target, but clarity still it is missing. So full clarity is missing here, and even other places also you can see here these leaves you can see. So all these things are clarity wise, you can say the left side one is the generated one and right side one is the target one. But no doubt there is a possibility to get the as good as the target. So it can even, it can improve the sometimes better. Let's say here in target case, let's say here some kind of hazy information is there, but due to processing of the generator, it can remove the haze here. So it can able to improve the situation. Okay, even ground truth is not ground truth doesn't even still having haze, but it can able to remove the haze also sometimes, because it is a convolution procedure. And then when it is targeting some areas, and it can work out for some other areas also, and those other areas maybe it will deteriorate or it may be improved. So it depends upon the requirement. If it is getting improved, so take it as advantage. If it is not it is kind of disturbed, so then you have to apply some kind of remedy to avoid that kind of disturbance. Generally, if you use the batch norm in the deep network for generation data, it will give the color distortions. It won't provide exact colors, and at edges it will give some kind of color distortion. So that color distortions is a kind of disadvantage, and uh, you have to apply some kind of measures. Measures is nothing but don't use batch normalization for data generation purpose. Use without batch norm if you perform. Even layer normalization or instant normalization is also not necessary. Even we have done batch norm, we have used batch normalization initial days of our GAN utilization, but later on we came to know that it is not performing good because color distortions are coming. That is the reason we have used the instant normalization. Later on we have totally ignored the normalization, and then we performed it, and it is performing better when compared to normalization. And then coming back to our discussion, let's say my target is like, if I am giving just simply just one green paint I put, and I'm giving it to the network, then it can able to generate the all greenery data. And then I did not specify whether I need mountain or not. So that is the reason it is giving some random content at the other region, like mountain regions. If I specify a mountain, so it is giving the mountain is adding in the each image. And I did not specify anything about sky color, so that is the reason it is giving different random color. But if I specify this is the sky color, it can able to give the sky color, and it can able to same color it is giving as a sky color, and then it can able to give. So do you think this is a kind of magic? So there is no magic here. Here also it is learning in that fashion. Network is getting learned, and your training data is like that. So your training data is like that. If you give green, means there are green data. If I give this color, it should apply on that particular portion. It will be like that. Means while training of your data, it is instructed in that fashion. If I give this kind of marker, it will take that kind of color. If I don't give any kind of indication, it will take any value, anything randomly. So now this is a architecture for the generative adversarial networks, GANs. So you can say this is a generator, you can say this is autoencoders. As I said, autoencoders are a generative models. So here on top of the autoencoder, which is nothing but generator, I'm adding a supervisor, that is a discriminator here. This is a discriminator block. And this is an, you can say, input image. This is an output, and this is a required ground truth. Real world images are nothing but ground truth here, my target. So both I am giving to the discriminator, which means supervisor. Supervisor is sitting, and supervisor having the knowledge of output, and then whatever the output is coming from the student, both will be evaluated, and he will say that no, your output is not at par with the required output. He will say that, and based on that it will be updated. Back propagation is performed on the generator accordingly, and then even while doing this also, discriminator will be updated. Back propagation is also performed for discriminator, because where discriminator is lagging, it should improve, because in supervisor case also he needs to improve his knowledge further, then only he can able to train the student. If he is having 100% knowledge on that specific problem, then there is no need of further improvements of the weight parameters of supervisor. But if it requires, he needs to improve himself. Okay. So by considering these points, we can go for the training. Let's say a small example case, like let's say one student has joined under me as a PhD student, and he has chosen some new topic, very new topic, which is I don't have much knowledge, or maybe very little bit knowledge with me, and but he wants to work, and I have given a chance that okay, go ahead, you work that. But I will say that let me read some content for 10 days, and then we will discuss. So so that time, that phase is nothing but supervisor is improving his knowledge. So which means back propagation is performing to the supervisor, and generator is doing whatever he want. He may be reading something, or maybe he is updating himself, or maybe he is not doing anything. After 10 days he will come. So there is no nothing update, or maybe small modification. If he need, he can do. But we will say here, there is no back propagation to the generator, and back propagation is performed to the supervisor, which is nothing but discriminator. And after certain level, like now once supervisor is to certain level, so he is good enough to supervise, then he will call the student, and he will discuss, and he will transfer his knowledge whatever he got from the readings, which are nothing but back propagation is performed to the generator with the knowledge of discriminator. Discriminator will means supervisor stop reading for the certain amount of time, and he will try to feed the knowledge to the generator through back propagation process. After certain process, both are good enough. Generator is also understanding the knowledge, means getting the knowledge, and discriminator is also getting. Both are working together. Like generator is getting the information and discussing with the discriminator, and whatever knowledge he has, a supervisor, he will try to, means both are improving by themselves and trying to solve the problem. Here the supervisor target is always that whatever the output is coming from the generator, which is nothing but student, and then already he has having the ground truth, so it will be verified, and based on that it will be decided whether it is at par with the ground truth or not. So which means when I give generator output as input to the discriminator, if it will say real, which means it is at par with the actual data, actual target. If it gives the fake, if it gives the fake, which means the generator output is not good enough to cheat, or good enough to, which is equivalent, which is not equivalent to the real data of the ground truth. So in that fashion, discriminator output is only the classification problem. It is classifying whether it is real or output. Whatever the input is coming to the discriminator, whether it is real or fake. In that fashion, it will be deciding. If it is generator output, if it is, it should able to pick the fake, and if it is real image, ground truth image, it should say that it is a real image. Means based on that, it is trying to get the knowledge about the real data, and then trying to analyzing the generator output, and based on that, it is trying to club to both are, it is clubbing. And based on that, it is giving the back propagation directions to the generator, and in the same manner discriminator is also performing the back propagation. So in this case, these are all the objective functions. I'm sorry, just 1 minute. Hello. No, 11:20 इनका भेज दीजिए. I'm in a meeting and then I will come. I will call you. Right now I'm in lecture. Okay, sorry. So here it is a kind of min maximization problem. Why it is min maximization? Discriminator is a maximization problem and generator is a minimization problem. Supervisor is always trying to identify the mistakes of the student. Means the discriminator is always trying to identify the mistakes of students. That means it is always trying to maximize the loss of students response, which means he is trying, through that he can improve the student. That's what his target. So that's why we call it as maximization problem. Loss maximization is performing at the student output. So that is the target of, that is the nature of the discriminator. That's why we call it as a maximization problem. And generator is nothing but whenever mistakes are identified, whatever mistakes identified by the discriminator, those will be considered and it will be improved by the generator. So loss minimization target is the generator requirement. That's why we call it as min max objective function is there. And then this is the objective function. You can say why it is taken, means you may get the doubt why it is like this. D of x and 1 minus d of g of z is required. Why not 1 minus of this and simple without that? So this is based on physical interpretation. I can explain why this happened or why they have taken this way. If I say discriminator is very strong in this case, if discriminator is very strong and x is a real world image here and z is an input image, this is an input image and this is a real world image I am giving as input to the discriminator, and g of z is nothing but generator output and d of g of z is the discriminator output when generator output is the input. Okay, so d of x is nothing but output of discriminator when real world image or ground truth image as the input to the discriminator. Okay, so in this case I said the discriminator is very strong. Supervisor is having knowledge of that research area. So in this he will say that as I am giving ground truth, it should decide that it should identify that is a ground truth only. It means 1, it will give 1. And here in this case it is a generator output, definitely it will give 0, which means log operation I am performing, it is just for uh, dimension reduction. Means it should not change the content very largely between the iteration to iteration in the training of the algorithm. That's why log is performed here. Log 1 equal to 0 and then here 1 minus 0, log of 1 minus 0 again 0, we are getting this is also 0, which means discriminator is good enough and it can able to, means this is objective function for the, if you say this is a minimization problem, maximization problem for the discriminator, and then discriminator is not required to apply any back propagation, whatever it is that is good enough. If I say discriminator is very bad, it is not good, which means it will give log of, which it will give 0 because it is giving the actually it is a real input, but discriminator I said it is not good enough, that's why it will give 0. Log 0 is a problem, that's why we will apply epsilon, which is generally in our case we are taking 10 power minus 12, 10 power minus 6, 7, like that we are taking. So once you apply the log operation on that, there is a content, some loss value is coming, that will be applying for back propagation and accordingly it will be performing. Here also it will be actually 1, g of z will be, d of g of z will be 1 and log 1 minus 1 it will be 0. Again epsilon will be added here, so that again it will be back propagated, means discriminator needs to be updated, which means back propagation is needed. So similarly this is the discriminator gradient calculation, this is a I'm sorry, generator gradient calculation, that is 1 minus d of g of z gradient calculation requirement. But here there is a vanishing gradient problem when discriminator is very confident but generator loss is not updating appropriately. I'm sorry, just a minute. Okay, so here this is the one. If I take this one is a generator objective function, if I apply discriminator is very confident, it is coming simply, it is 0 is coming, it is 0 coming, and log 1 and 0 is coming, and if I apply this back propagation to the generator, no back propagation, because log 0 is 0 only, log 1 is 0 only, there is no back propagation. That's why we are taking this in terms of gradient 1. Gradient is nothing but derivative only. Log 1 minus d, I am just considering this is a sigmoid output, because you can say at last I am using sigmoid activation function or maybe relu. Just for understanding, I am taking a sigmoid case. So log 1 minus sigma. So if I apply this log x kind of thing, it will be 1 by x into derivative of this x, which is nothing but this particular portion, which means derivative of sigmoid is again sigma into 1 minus sigma you are getting. So that is the case, and both are going off, and you are getting this is minus sigma, which is nothing minus d of g of z is coming, even if it is 0. So even discriminator is confident, epsilon term is there, and it will be back propagated. It is working. Okay. So in that fashion, it can work out. And coming to the advantages of the generative adversarial networks. So advantages of generative adversarial networks, I said it is training phase, it is better than the autoencoders, but still there are an issues with the generative adversarial network may fail. These are all the failure cases. You can say it may diverge sometimes. It is means it is better than the autoencoders. I am not saying it is the best among, means up to GANs, means after autoencoders GANs have come, and that is the best one. And now in GANs case also they are adding some transformer layers, it is increasing the further transformers are there, it is improving. But GANs and transformers are not in same phase. Yes, transformers is a kind of layers we are using with meta content, metadata, so that it is able to improve the accuracy. Okay, these are all the kind of failure cases for the generators. And then to avoid this, we need to go for mini batch size, and other one is like with labels at this discriminator case. In discriminator, instead of giving only real or fake, we can go for the uh, other labels also, like this fake one is as it is and real is what, like that you can able to make it. So that way you can able to improve this accuracy. And these are all the alternative equations, like objective functions. If you take in reverse, you can get these functions. It is opposite only, there is no much difference. That's why I am taking this segmented output, and if you need reverse, that is also possible. And if I give, this is the input image and this is the synthetic image generation, or synthetic image to actual image generation, and so on, and black and white, which are nothing but grayscale image to color image generation, and then Google maps, like you can say structures to the maps, and then day to night or night to day, like that you can able to do all this kind of stuff with the requirement, like if this is an input and this is a target, then you can able to okay. So I can give the one example for image restoration, which is nothing but fog removal. So let me give this example. So this is a kind of how hazy image or foggy image is generated. Let's say this is an input. This is a basic image processing concept. Let's say this illuminated light is means this object is illuminated with a source of light, and then illuminated light will be reflected back, and it will reflect in all 360-degree direction. But this, it will reflect in all directions whenever illumination is there. Illumination is hits the object, and then immediately it will start reflection. It will start reflection. If let's say this is a reflected light, and I'm keeping the camera sensor here within the line of sight of the reflected light, then it will capture that side only. Because if I am giving this kind of a hand, you can say this particular portion only, backside you are not able to see because this light is reflected the other side and camera sensor is not there in that side. That is the reason you are not able to see that. So in that way, this image formation is happening. So while image formation is happening, the reflected light needs to travel for a certain distance through air medium, and here there are the dust particles or water particles present in that, and then this reflected light hits that, and it will attenuate. This reflected light will attenuate, and attenuated light will be traveling. That is nothing but J into T. T is a transmission map, which means the distance between the object and the camera sensor. And similarly, so annotated light, as it is losing the energy, it is energizing the either water particle or maybe dust particle, and that reflected one itself behaves like a local light source, and it will also move towards the camera sensor. Both will be coming because of that hazy image. If this is actual reflected image from this object, and it is traveling certain distance, so this is a kind of transmission map. It depends upon the distance, and then this is a content we are getting. So this is a kind of equation, and then we have developed a deep learning network with end-to-end fashion training and with different types of modules, residual and inception modules. And we also use the SSIM loss and edge loss, various losses. And this is a generator network we have used, and this is a discriminator network we have used. Based on that, we have trained, and this is a kind of inception or followed by reception module, residual inception module. And these are all combinations are there here in this network, and the network is got trained as per the requirement which is given. As it is a part of competition, we have used some images given by the organizers, and we have done it. And this is ours. We got it secured a 10th rank in terms of PSNR and SSIM. And now coming to the experimental results case, once we try in this is an input hazy image, and these are the results we got from existing method. This is the result of our proposed method. From this you can clearly understand our method is able to give the better, means can able to restore the data in very appropriate manner. Similarly, this is also an image. These are all the computation images. We don't have any ground truth for this. So these are all the results. Here also you can see it can able to, it's a very dense haze is there, but still it can able to restore the data in very appropriate manner. You can say it's a kind of contrast adjustment process or image restoration problem. And here we felt that maybe this data kind of this kind of patches or this kind of content may be there in the training data. That may be the reason we are getting good results. That's why we have taken one image which is simply downloaded from the internet, and this image, these are the results by existing methods, and this is our output. From this it is clear that ours is performing far better than existing. And again we have taken another image, and these are the results by existing, and this is ours. So from this we can say our method is able to give the better output, better restoration, and it can able to increase the visibility. So this particular system we are making in hardware setup, and we are maybe it needs to be launched by coming March, but because of pandemic it needs to be extended for maybe for another 6 months, and it will be we are making hardware and we are going to launch it. And here it is a conclusion case. So here we have proposed, we have discussed about the generative adversarial networks. Before of that, we have discussed about autoencoders, and we have discussed one application of haze removal in detail, means with kind of network architecture, all these things. And we also discussed various applications of generative adversarial networks. If you are having any questions, I think we can take up the questions in 5 minutes.
Yeah, uh, thank you, Doctor. And it was a nice session on GAN, and even I like the way you explained the applications area over here. Okay, so to participants, if you have any doubts, please you can ask. You can raise your hand or ask in the chat box. Okay, there is someone who raised hand. Can you unmute who has raised hand?
How to use GANs for image classification? No. Yeah. For classification, we cannot use GANs. I simply said that GAN is a generative model, generative adversarial network. It is a kind of data generation. For classification purpose, we won't use the GANs. And could you please provide some thoughts on using encoder decoder or GAN model for domain specific text generation? If domain is small and expecting a good accuracy, does this kind of architecture provides a genuine support for such models? Yeah, text generation means even what should be the input here? Text generation is possible, but based on your input. Even there are different types of GANs are there, even audio based GANs also there. Input is an audio and output accordingly. If you give input based audio like generate Taj Mahal image, so it's an audio, and then based on that it can able to generate the image. Same manner, if I am giving image, it can able to generate the text also. For text to image generation, the input will be text only or image only, image also. Yeah, even it can be audio, or if you means audio means having, it needs to convert it into text only, then only it can able to. Like I'm saying that please generate the Taj Mahal image. So that time what it happens, it will understand the Taj Mahal is requirement, means it is a NLP is required, that whatever text you are giving, that text needs to be understand using NLP, and then based on that it will understand, and based on that it will generate the your required image based by collecting the content in the training content. Like those Taj Mahal content should be there in the training, and based on it can able to generate. Text to text generation, text to text generation means what should be the target. You can give some text and it can able to predict, means it can able to generate elaborated text also. In that fashion, if you can train your algorithm, it can able to generate. Autoencoder cannot be used in classification problem. Yes, directly autoencoders we cannot use for classification problem, but there are one or two papers are there. What they did, autoencoder like encoder decoder architecture is there, and in that what they are doing, input is an input image, like input image we are giving, and output should be same as the input. It is got trained, and after training of the algorithm, decoder will be discarded, and encoder portion is considered for feature extraction purpose, so that you can able to go for the better feature extraction, and that extracted encoder output content is considered as a features, and based on that you can go for the classification. That way you can do, but directly we cannot use autoencoders for the classification problem. And if that is the case, transformer model use this encoding and decoding mechanism for classification. Encoding is there, and decoding itself is a kind of transform, means it is not exactly data regeneration. This is not exactly data regeneration. So even in encoder itself I can divide into two things, like now one is a encoder module dimension reduction, other one is like further adjustment in that. They say they might have named it as like that, but classification case decoder is meaning is like in my explanation, data synthesis or data regeneration or data restoration. The data restoration case, in we can use GAN, but classification case we cannot use. Can we use encoder decoder GAN for NLP? Yeah, there are cases. I think you can go through those GANs for NLP purpose and you can use it. Yeah, this PPT also I can share. I will share with the organizers and they can share with you.
Sir, good morning, sir.
Yeah,
Sir, how?
Yes, please.
Yeah, sir. How unit can be used for image reconstruction, sir?
Unit, na?
Yes, sir.
It is very simple. Unit case I have given segmentation one, but input means unit case downsamplers followed by upsamplers are there. So in that, if you go for supervised learning, that is the reason I explained for what is supervised and what is unsupervised. In supervised learning, input is the like your algorithm is for what application you are saying?
Sir, for video anomaly detection,
Yeah.
if you spatio-temporal unit,
Yeah,
sir,
exactly.
in general,
Yeah, please complete.
Yeah, so generally we do the image reconstruction, and we will find out the MSC loss between the input image and output image, sir, in the autoencoder model. But coming to the unit, we have skip connection between first layer to nth layer and second layer to n-1th layer, sir. So if we apply the same spatial temporal mechanism, due to these skip connections may affect the image reconstruction, sir. Is it affects or?
No, it won't affect. Actually, these skip connections are given to improve the output. Skip means if skip connections importance is there for your application, it will utilize the skip connections. Yeah, means weights accordingly will be developed. If skip connections importance is not there, definitely weights will be very low. It tends to 0. Your network itself will tune those weights accordingly. And
so
for,
okay, sir.
Yeah, for anomaly detection, input is your input video, output is the that regions wherever anomaly content is there, it should be highlighted. Am I right?
Yes, sir. So one more thing is, if you have a architecture unit like encoder followed by LSTM, and after that if you have decoder layers, then if you have directly skip connection between encoder and decoder bypassing the LSTM, is it okay, sir, then?
Yeah, it is fine. I am telling one thing. Skip connections will be either concatenated, generally concatenated with the content. So whenever you are concatenating, if your algorithm is disturbing because of skip connection, let's say, if it is happening, let's say, that time automatically weights belongs to that particular skip connection content will be 0. It will be tends to 0, so that importance of that particular connection will be ignored. But majority cases that content is also required, because your LSTM may not be whatever algorithm you are performed for long term and short memory LSTM, it may not be very appropriate. It may not be enough to give the data regeneration. There may be loss of information that will be recovered from the skip connection. That is the intention.
Okay, sir. Okay, thank you.
Yeah. Ragachari, you have raised your hand. Can you ask your query?
Yes, sir, it's me. Just now I asked the question.
Acha, sorry.
Okay.
And one question is, does transformer use autoencoders for classification? Classification, autoencoders meaning I have explained. And some people may write on autoencoder name. Autoencoder means, like, you can say only encoding module may be there. So decoding and data synthesis, only one thing I am telling, my explanation is autoencoder meaning is that data regeneration is there. That time I am saying autoencoder, but their case maybe data encoding is only there, and that's why they are calling it as autoencoding module, and they are performing it for classification. That is possible. It depends upon the naming. So paper to paper naming is changing. You have to be very, very cautious while reading the content. Transfer learning means, in this GAN you will apply transfer learning, or this GAN content you will use for transfer learning? After training of the GAN, this content you will use for transfer learning, or while training of GAN you will use the transfer learning of other networks? Both are useful. GAN content, yes, that's what I am telling now. Autoencoder trained and encoder module is only considered for the feature extraction. That itself called transfer learning only. It is possible and it is beneficial also. There are, I think, 2-3 papers in that kind of processing. Okay. Any other questions? Thank you so much.
Okay. I suppose there are no more questions. Okay. And thank you so much, Professor, for accepting the invite and also delivering this session at WADLA. Thank you so much.
Yeah, thank you so much, ma'am, for inviting me for this, and as well as I would like to thank Dr. Rakesh. I think he is not here, for the invitation, and thank you so much. I think if you are having, if participants having any doubts, I think either you can send an email to me. I will share my PPT with organizers over the email. Based on that, I think if you are having questions, you can contact me.
Sure, sure. That was nice. Thank you so much. Thank you.
Thank you so much. Now, one more question is there. Tone detection is there. Detection is a kind of classification problem, or even location. So it's a kind of classification detection one. So if it is simply saying that detection, sorry, classification cannot be done with GANs, and regression can be done with the GANs. This is only the answer, straightforward answer.